have now seen two examples where we have been able to compare proportions. We have looked at one sample proportion inference, and we have done a simulation study, and we've done a one sample z-test. And we then, in our last video, we have looked at a simulation study where we have had two categorical variables, one an explanatory variable and one response variable, and we did a simulation study there. What we're going to now do is look at the theoretical sampling distribution of the difference of two sample proportions, p1 hat and p2 hat, and under the conditions that we can use that statistical theory to describe the sampling distribution. So remember, a distribution is described by its center, its spread, and its shape. So we're going to take each of those things in turn. So our sample statistic, as we'll recall, is p1 hat minus p2 hat. This is our sample effect, how different the two sample proportions are. So we have a categorical explanatory variable, which defines the groups 1 and 2, and we have a response variable, a categorical response variable, and it is the proportion of successes, so the proportion of success, so the proportions of a given level for the response variable in those two groups 1 and 2 that we are interested in comparing. So under what conditions can we use a specific center, a specific spread, and a specific shape to understand the distribution of this difference of these two proportions? So we would like the true mean difference in proportions to be defined by pi 1 minus pi 2. So if our statistic is p hat 1 minus p hat 2, in the population, the true difference is pi 1 minus pi 2. So this is going to be our parameter of interest. We know it's a parameter because it is Greek letters. For the null hypothesis of no difference, this true parameter would be pi 1 minus pi 2 equals 0. The true difference would be 0. In our simulation, when it says the simulation above, this is really the simulation in our previous video. This is consistent. We set up the simulation so that the true mean difference in the long run would be equal to 0. So if we were to refer back to the simulation results before, the mean sample difference, or the mean of the differences of those 1,000 simulated samples that we did, had a mean in the long run of about 0. So that is consistent, and we designed the simulation on purpose so that that would be the case. In order to get this true mean difference to be 0, the condition required is to have random samples. So we would have to randomly sample from each of these two populations, group 1 and group 2. And that's especially true if we're doing an observational study, or if we're doing an experimental study, we're going to have to do randomization, which would be the random assignment to each of those two groups, group 1 and group 2. For the earlobe crease and coronary artery disease study, this was a observational study. We cannot randomly assign people to have coronary artery disease or not, so we had to randomly sample patients who did or did not have that disease. And if that condition is true, if we did randomly sample from those two different populations, those with and without coronary artery disease, in the long run, on average, the difference in these proportions should be 0. The next condition is that the population spread, the spread of this difference, p1 hat minus p2 hat. So remember, this is the standard deviation of p1 hat minus p2 hat. Remember, we're talking about the standard deviation, or we're talking about the distribution generally of p1 hat minus p2 hat. So the center of the distribution of p1 hat minus p2 hat is pi 1 minus pi 2. On average, the sample difference should be the population difference, pi 1 minus pi 2. The variability of the sample difference, p1 hat minus p2 hat, should be summarized by the square root of pi 1 times 1 minus pi 1 over n1 plus pi 2, 1 minus pi 2 over n2, where pi 1 and pi 2 are the true proportions of the respective groups. When we don't know pi 1 and pi 2, so this is when pi 1 and pi 2 are unknown, we have to use some sort of estimate. So that might be something like square root of p1 hat 1 minus p1 hat over n1 plus p2 hat 1 minus p2 hat all over n2. This whole thing is under the square root. So that is p1 hat 1 minus p1 hat over n1 plus p2 hat 1 minus p2 hat over n2, all under the square root. So if I don't know pi 1 and pi 2, if I don't know the population parameters, and believe me, we usually don't, the best thing I can do is estimate them with the sample proportions p1 hat and p2 hat when pi 1 and pi 2 are unknown. But we have something interesting. For the null hypothesis of no difference, that is when pi 1 minus pi 2 equals 0, which is the same thing as saying that when pi 1 equals pi 2, we can simplify this. We're saying that in the population, the true proportion for the first population is the same as the true proportion for the second population. That is, the probability of having an earlobe crease if you have coronary artery disease is the same as those for people who don't have coronary artery disease. That is, it's the same proportion. So it doesn't matter what group you come from. You're going to have the same probability of having this earlobe crease. So rather than calling it pi 1 and pi 2, we might just call it pi, this probability. So when that's true, we're going to do something called pooling. So when the null hypothesis is true, we're going to use this pooled idea of p hat 1 minus p hat times 1 over n1 plus 1 over n2. This works because if p1 hat is a reasonable estimate of pi 1 and if p2 hat is a reasonable estimate of p2, that is, if I've taken random samples that are reasonable representations of the true populations that they come from, then p1 hat and p2 hat should be estimating the same thing, and I should be able to pool that information together to estimate this constant thing. Pi 1 and pi 2 should be the same thing as well. So p hat is really just the total number of successes over the total number of observations. In our example from the previous video, this would be the total number of people with earlobe crease over the total number of people in our sample. In this case, we want to know if it's consistent with the simulation above. This would be the p hat of people with earlobe crease, and that's the total number of people with earlobe crease. In our sample, there were 48 people who had earlobe crease if they had had coronary artery disease, and there were 9 people who had an earlobe crease and did not have coronary artery disease. There were 110 total people in the sample. So this gives me a pooled p hat of 57 over 110. So in my sample, there were 0.518, there was a sample proportion of 0.518, or about 51.8% of the people in the sample had an earlobe crease, regardless of whether they had coronary artery disease. So this means that my standard error for p1 hat minus p2 hat can be found using this pooled p hat. So I'm going to use 0.518 times 1 minus 0.518 times 1 over n1, which in this case was 80. There were 80 people with coronary artery disease, plus 1 over 30. There were 30 people without coronary artery disease. And that gives me a standard error of 0.107. If we refer back to our simulation results, we had a standard deviation of 0.11110, and within rounding, this is equal to the standard error that we got here. The standard error of p1 hat minus p2 hat is the standard deviation of our sample difference. So this is roughly equal to the standard deviation of the sample difference we got from our sample statistic, or from our simulation. So yes, this is consistent with the simulation results. The last thing that we have, so when is this valid? Well, we can get this spread when we have independent samples. So this is valid for the independent samples condition. I can add under my standard error when I have independent samples. If I don't have independent samples, that is, if my groups are not separate from one another, or if someone can both have and not have coronary artery disease, or if I've done a within subjects design, a repeated measures design, or a matched pairs design, then I cannot use the standard error. I cannot use the standard deviation formula, and I'm going to have to do a different approach to my analysis. We don't cover that analysis in this class. It's called the McNemar's test. You can read about it in the book, but we're not going to cover it in this class. So we're identifying the conditions that get us to the theoretical sampling distribution that we would use for our test. So random samples allow us to assume that the true difference is the true difference in the proportions. Independent samples allow us to use the standard deviation, or the standard error that we've identified. And finally, we want to be able to assume that we have an approximately normal sampling distribution. So we are assuming approximately normal. That is, the z distribution is appropriate. I want to be able to use a z-test in this situation. So, is this consistent with the simulation above? It's not. So the simulation, if you refer back to the previous video, did have a unimodal and symmetric shape, which is awesome. However, in our case, we can't assume this. Why is that? We need to satisfy the condition that we have at least 10 successes and 10 failures in both samples. So we actually have to check the condition here. So we need a big enough sample in each group. In this case, we need the coronary artery disease and the non-coronary artery disease samples, both of those samples, to be big enough so that there are at least 10 successes and 10 failures in each sample. If we were to write that out, we would write that as n1 times p1 hat and n1 times 1 minus p1 hat, n2 p2 hat, and n2 1 minus p2 hat are all at least 10. If we were to go back to our data, and I'm going to scroll back to that for just a moment, so bear with me. If we go back to our data from our previous set of notes, we can see that we have 48 successes in the CAD group in group 1. We have 32 failures in group 1. That is, we have 32 people who do not have ELC in group 1. We have only 9 successes in group 2. There are only 9 people who do not have ELC but who also don't have CAD. So in group 2, people who do not have coronary artery disease, there are only 9 people who do not have earlobe crease. There are 21 successes in the second group, or 21 failures in the second group. So among people who don't have coronary artery disease, there are 21 people who also don't have earlobe crease. So we have 10 successes and 10 failures in group 1. So there are 48 and 32 successes and failures respectively, but there are not enough successes in the second group. We only have 9 successes and 21 failures in the second group. So because there are only 9 successes in the second group, we have not satisfied that condition. We need at least 10 successes and failures across all 4 categories. So in our case, we can't assume this. So We have not satisfied this. We don't, or do not have big enough samples. Specifically, sample 2, the non-CAD group, the people without coronary artery disease, is not big enough. So we cannot assume the normal distribution. And by doing this, the p-value that we get when we look at the simulation is not going to be quite as same as what we would get under excuse me, as what we would get using the theoretical distribution. But altogether, these are the conditions for a two-sample t-test, or excuse me, a two-sample z-test for comparing two proportions, and what they get us in terms of the sampling distribution. So the sampling distribution is the true difference in proportions pi 1 minus pi 2, with the standard deviation, the square root of pi 1, 1 minus pi 1 over n1, plus pi 2, 1 minus pi 2 over n2, and it follows the normal distribution when we have big enough samples from both groups. We have to have independent and random samples, and we have to have at least 10 successes and 10 failures in each group. And of course, as we mentioned before, we have to have a categorical response and a categorical explanatory variable. So these are the conditions and the sampling distribution for comparing two proportions. In the next video, I will go through an example where we do satisfy all the conditions required, and I'll show how to conduct a two-sample z-test, and then another video where I do a two-sample z confidence interval for comparing proportions when these conditions have been satisfied.